So thank you for inviting me. Welcome to Sorbonne University. So I'm Julien Laurat. I'm professor of physics indeed at Sorbonne University. So here I'm leading a research group at Laboratoire Castres-Bruxelles on quantum optics and on quantum information network. So we are developing many capabilities in my group related to quantum network. So we are developing mainly on the theoretical aspect, many witnesses for non-classicality, for instance. We are developing also the light sources that can be used in a network, so from cat state to entanglement. And another focus has been for a long time the development of light radio interfaces, and in particular quantum memories for light. So where you would like to store an optical photon, an optical qubit, or entanglement, if you want, into a quantum memory. So I will focus on that today, and I will focus even more on a recent work, which is not yet published, actually, soon on archive, where we demonstrated actually a quantum money. So I've seen that just now. I don't know where it's coming from. This quantum money.
Stickers.
Okay, that's a nice sticker. So that's a quantum money. So we tried actually recently in the lab using a quantum memory to do a new version of this experiment where you can generate quantum money with a storage file. So I heard at the beginning that quantum memories are far away, they are basically not existing. They are existing, they are commercial products since last week. So I'm also the CSO of WeLinq, and I will show you that at the end of the talk. So let me start by this. I mean, we already had introduction to that. I like this picture of what will be a quantum architecture in the future, in the near future. This is coming from a roadmap from our US colleagues about the development of quantum interconnects. And you can see many use cases, which are, most of them, related to networking. So you may want to make networks of sensors, you want to make cryptography on long distance, so you want to distribute entanglement. This is a QR, that's a quantum repeater. You want also to develop some quantum data center where, at the end of the day, you will scale out quantum computing by networking quantum processor units. Now we come back to this application also later. But central to this picture is the use of quantum memory. So you need a kind of a buffer where you can indeed synchronize information, exactly as you have in the classical world. So you would like a system where you can have an input quantum information, you store it into a matter system, and later on demand, you would like to retrieve this information. So there is a large variety of applications. So as I said, the memory is a buffer, it's a synchronizer. So you might want to use many photons which are probabilistic, and then you can synchronize them thanks to this quantum memory. You may want to enhance also a quantum processor unit just by adding a memory to it, and there was paper recently by Nicolas Amboise, for instance, that can show you that if you take some quantum algorithm, you can really improve the number of required qubits in your QPU to make this quantum algorithm run. And then the two main application is, I would say, in terms of networking, quantum repeater. You want to distribute entanglement at a distance for connecting QPUs, it can be blind quantum computing, for instance. But you want also to develop this idea of a quantum data center where you have multiple QPU which are limited in size. This is what is happening today. We heard before for neutral atoms, maybe 10,000 is a good number in a few years. But at a certain point, you will like to connect them together, make all them together in a distributed fashion. So some multi-core quantum distributed quantum computing. So that was a very general introduction where memory is part of the game. And I would like just to give you today to highlight how we can make actually highly efficient optical memories, how it became a commercial product. And then this demonstration of this QKD primitive, which is a quantum money that we did recently in the lab. So let me start by the quantum memory. So again, what is a quantum memory? It's a matter system. So you want atoms. Here it's a picture of cold atoms. I will come back to that, but there are many other platforms. And I want to map a photonic excitation to an atomic excitation. So I have to have an input, which is my photonic qubit, map it into this device and read it out and preserving all the properties and during a long lifetime. So the classical picture I'd like to give you is if you use a large number of atoms, it's like a picture in classical electromagnetism, it's like an array of antennas. So if you have many antennas, like this one actually, who are all working together, so if they are in phase, then you will have a very directive emission. Okay, and then today, the 5G and 6G are also pushing this kind of antennas to be very directive, for instance. This is exactly what we are doing with atoms. I'm working with billions of atoms all together. And if I know how to control them well, there are spins, there are many antennas, they are going to radiate. This emission will be in a very well-defined spatial-temporal mode. So that means I can come with a single-mode fiber, store it into my memory, read it out, and it's going to be emitted in a very well-defined direction, even without a cavity. And this collective effect will give me the light into single-mode fiber. So I can go from single-mode fiber to single-mode fiber, but having this storage in the middle. The name of the game when you work with quantum memory, as we said, is the synchronization. So the name of the game is the efficiency you can achieve with this kind of device. So eta here is the storage and retrieval. I store a photon. What is the probability to get the photon out? And I give you here, let's say I want to synchronize m photons all together. So this is the gain relative to no memory boost. So as you can see, when I increase the number of QPUs, for instance, involved, with an efficiency of 20% or with an efficiency of close to 1 or 90%, the gain is orders of magnitude, here it's 10 to the 10, when you increase the number of QPUs you want to connect. So that's the power of synchronization, which is given by these quantum memories. And this is also what we find in the example of a quantum repeater. A quantum repeater is a chain of quantum memories. The goal of these memories is to have an asynchronous preparation of the network, and then the scaling is given also by the efficiency of these memories. With no memories, you have an exponential time for communicating over long distance. You will be polynomial or sub-exponential if you use a quantum memory. So this is coming for the same reason. So let me show you how we can do it. So the typical system we would like to do, I don't know if you see it, is to use many atoms and trying to really have a strong interaction between the light you are going to send and the atoms. So what we are doing is to start with many atoms.
The preparation of the memory begins by cooling entropy in the atoms via lasers and a strong magnetic field gradient, forming a dense centimeter-long elongated cloud. This technology doesn't need any cryogenic system. It is operated at room temperature thanks to this efficient laser cooling. At this step, the trapping fields are switched off and the control laser is switched on. The memory is now ready. A single photon, operating from a quantum computer or a quantum network, is then injected into the memory and stored by switching off the control beam. When needed, the control beam is switched back on, triggering the emission of the photon on demand, restoring it to its original state.
Will go out. So it's really something you can control on demand via lasers. So what you need to do that if you want to be highly efficient, again, you need many atoms. And I started to work on quantum memories 20 years ago. I was at Caltech as a postdoc, and we were doing first proof of principle of quantum memories at that time. And for a very long time, the storage and retrieval efficiency was limited to something like 10, 15, 20%. So most of the time, you are losing the photons. And in 2015, so almost 10 years from now, that was still state-of-the-art. So at that point, we decided to revamp completely our experiment on trying to increase even more the number of atoms we have in our experiment here in Paris. So then we end up with a very specific magneto-optical trap. You can see a picture of the experiment in the lab. You take a half a room like that to make, because there are many lasers. There is a vacuum chamber, and inside the vacuum chamber, you can see this 3 centimeter long, which are billions of cesium atoms at very low temperature, a few tenths of microkelvin, and with a very large, what we call OD, optical depth, so very large number of atoms. So that enabled, finally, in 2018, to make a first paper where we were storing a single photon on the polarization qubit. The fidelity was 99%, so that means there is no added noise in the process. But more importantly, the storage and retrieval efficiency was close to 70%, and it was doubling the state-of-the-art at that time. So we were very excited by this result, but actually it was only, in a certain sense, 70%, and there was no way in the lab to get better. We had worse, we can increase the number of atoms, and it was getting worse. So we were a bit disappointed. And to make the story short, we understood then that our atoms are very complex, there are many energy levels, you have to take them into account. So that led to change again the experiment, and finally, 4 years ago, in 2020, we achieved a quantum memory with a 90% storage and retrieval efficiency. So we were even able in this experiment, so that was done in the ramp phase of the flagship, the KIA, the Quantum Internet Alliance. We were able to make entanglement between two quantum memories, so store entanglement, and retrieve the photonic entanglement, and preserving this entanglement with 90% efficiency. So now we are using this device in KIA, in the new phase of the flagship, where the goal now is really to develop a pan-European entanglement-based network. And the goal now in this phase of the project is by next year to have a 50-kilometer link where we distribute entanglement. And this is ongoing in the lab a few meters from here. The next target, which will be the next phase of KIA, which is going to start next year, will be to go to 500 kilometers by the end of the decade. So I don't want to focus too much on this Quantum Internet Alliance, which is ongoing here, but now come to our demonstration of quantum money. So you know, even likely better than me, what is quantum money. So that was one of the first primitives for quantum cryptography introduced by Wissner. And there was a first demonstration with a security proof in the group of Eleni Diamanti, so here, a few years ago. So the idea is you are going to take this banknote here, which are actually your photons, send it to a client, which will going to give it to a vendor, and then the vendor, by communicating with the bank, can certify the transaction. And then you can avoid any double spending. And this is guaranteed here by the law of physics. So Eleni did an experiment a few years ago, an all-photonic experiment, where you have pulses of light, polarization control to encode the information, and then, this is the vendor, you are measuring in different bases the polarization qubit, you communicate with the bank, and you can verify that there was no double expense happens during the transaction. And she had also a paper about what we can do if we had storage into the game, which would be the case with quantum money, you would like indeed to store it. So we pushed that recently a step further by trying to include in this kind of very demanding protocol, actually, if you want to check the security of the system, it's very demanding in terms of noise and in terms of loss, and it's not robust against loss. So what we wanted to do is, let's try to add in this generation measurement, as we had before, to add now a memory layer in this exchange. And we have been able to do that, thanks to the memory we have now in the lab. That wouldn't have been possible with the previous version of memories we had over the last 10 years, because you need, at the same time, a very high efficiency and a very low noise. So this is typically what you get. So if you check as a function of the error rate you have over the whole protocol, the whole transmission, and the memory efficiency you have, there is a very small corner here where you can verify the security, the unconditional security of the protocol. And actually you see you need a memory which is at least 60-70%, and you need an error rate which is well below 4 or 3%. And finally, it took us quite a long time. We have been able to put a point here, an experimental point, where we are indeed in the security region with storage of the information. So I think that's the first demonstration of a quantum cryptography primitive where indeed we have storage in the game. And it's also showing you that we do have now devices which are performant enough to be pushed for other applications, and in particular for distributed quantum computing. So in just 1 minute left, I would just speak about a little bit about WeLinq. So all these developments, the work we did on quantum networks, the work we did on quantum memories, on sources, pushed to, now already 3 years ago, to the foundation of WeLinq, with Eleni Diamanti and Tom Darras, who is the CEO of the company. So WeLinq is based in Paris. There are 30 people there working in the company now. And WeLinq is a networking company which is developing network capability to push the scale-up of quantum computing on quantum network. So we had the first product, which has been announced last week, so QDrive. So this is a quantum memory. You can buy it now. It's everything is included in this 19-inch rack. It's a fidelity above 99% and efficiency above 90% on 200 microseconds of lifetime. And if you go to the LinkedIn page of WeLinq, you will see the video online where all these developments are presented, and also the use case we are targeting now. So in WeLinq, we are really targeting the orchestration of future quantum data centers. So in such quantum data centers, you will have cluster of interconnected QPUs, and for that, you need to develop many capabilities. You need to develop the algorithm part we were discussing before. You need a distributed quantum computation compiler. And actually, we do have it. So we released recently Arachne, which is the WeLinq compiler for distributed quantum computing. You start from a monolithic algorithm, and then you find a way, given the number of links of entanglement you have, given the number of QPUs you have, the best way. So that's a lot of circuit cutting at the beginning, how you distribute this algorithm over a cluster. You need also to have architectures, protocol, to share the entanglement, which can be different from one QPU provider to the other. And then the hardware, where you need to develop all this photonic network capability with storage capability to be able at any time to allocate entanglement in such a network. So we are working already with many QPU providers because we want to be hardware agnostic. So if you want to look into this cluster, you need to be able to make entanglement between the QPUs, but there is a missing step, which is also how you extract a photon from a QPU. You need a QPU to discuss with the network. So we are working on that. We are working on this photon extraction with Pascal on neutral atoms, with QFOX in Delft, about superconducting qubit on the transducer, and Candela on the photonics QPU. So thank you very much. I will stop here.
We have time for just one question.
Okay, I'll make use of the time. So just one question. In quantum cryptography, a lot of the security guarantees come from the fact that quantum information actually acts like a resource, right? It cannot be copied and it cannot be, it cannot be cloned. If I understand correctly, your approach to memory consists in having many atoms and many photons that excite them. So I guess you end up with a big number of copies of the same state, right? So how do you ensure that these resource-like property of quantum is preserved in the setup?
So actually the experiment is, the device is many atoms, but it takes one photon at the input, or one qubit at the input. But let's say you have one atom. If you send one qubit on it, you can absorb the light, and then when you read it, it's going to be emitted everywhere. And if you need then to put eventually a cavity to collect the light and so on. Here it's a full free space approach, where you have these billions of atoms working all together. You absorb in a coherent way one photon, one photonic excitation, and this one is going to be delocalized over the billions of atoms, like my billions of antennas. And then when I read it out, they all work collectively and re-give me one photon. So there is no cloning at any time in such a quantum memory.
Yeah, I was missing that it was just one photon.
Yeah,
okay,
just
perfect, thank you.
Okay. For how long can you keep the memory? Just what's the scale?
So this first product is 200 microsec, which already means more than 50 kilometer distance. The next generation soon will be 1 millisecond.